Hello, everybody. Thanks for attending. A little bit of a personal introduction, first of all. My name is Daniel Cabezas. I work as a pen tester in Ernst & Young, Melbourne's Advanced Security Center. As you can quickly notice, I'm not an Aussie, I'm Spanish. So please take that in account. I may sound a little bit strange. This is the first presentation I do in English. And feel free to shout at me if whatever I say becomes weird. I don't know. So what are we going to talk about today? The aim of this presentation is to give an overview of the different classical file comparison analysis techniques and their limitations when facing the task of determining if a set of files come from the same source, from the same origin. Despite we will focus these techniques on source code reuse, so detecting if two different binary executables come from the same source code, some of the techniques that we'll see can be applied in different scenarios, and well, we'll see it later. I warned you, most of the presentation is quite boring. So we'll quickly present, first of all, the well-established, well-known, old-fashioned techniques for doing file analysis and comparison. Blah, blah, blah. And unfortunately, most of these techniques have a lot of serious limitations when dealing with investigation of IP infringement, intellectual property. In this case, the typical case is for a security analyst to determine if a set of files, say A, have been copied or leaked or come from the same source code that was used to generate a set of files B. So first of all, let's go to a very, very high-level overview of how does compilation work. How do we create a computer executable? The procedure to use to create a new application is called compilation. I won't go into details. Basically, everybody knows. You have a bunch of high-level instructions in a language like C, Java, or whatever. You use an application called a compiler, and that will generate our program because it translates those high-level instructions in zeros and ones, because that's binary, and that's what binary that language computer speaks. Of course, this is not a straightforward process. Compiler has to deal with a lot of different stuff, different architectures, different architecture means mobile, an Android mobile doesn't speak the same binary language as a Mac OS X laptop. Different compilers generate the code in a different way. There can be optimizations, etc., etc. So even the same input files can generate a completely different looking final object code. What does it mean? Well, it means if the same source code is stolen and reused, even the same code, they can look completely different when compiled. If the infringing party source code is not reachable because, well, basically when you are suing someone and saying, oh, you stole my source code, they are not going to show it. So we'll have to deal with it and do something more than just look at the files. First of all, let's revisit some of the old, well-known techniques of file analysis. Plaintext analysis are very well-known techniques. They are often used to debug code, look at log files, check for errors, etc. It's really simple. Just open two files and into Windows and go line per line and say, oh yeah, there's a difference there. When dealing with slightly more complex scenarios, very big files, you can find programs like diff that will especially highlight which are the difference between one line or the other. So the good thing, these are very well-known techniques, and they can spot a similarity, or they can spot that someone stole your source code very easily if no one's trying to hide. Of course, the worst thing about this is that this works on file per file, so you have open one file on a window, open another one in another window. But when you have a bunch of files, say 100 files to be compared, it takes a little bit more time. And if you don't have access to the plain text, there's nothing you can compare. Let's review the basic binary comparison techniques. There are basically two, binary diffing and hashing. Binary diffing is nothing more than applying the same technique as before, but with a binary file. So we use an hexadecimal editor or something that can highlight the difference in a byte per byte basis, and we spot which are the specific offsets that contain a difference from one file to the other. Hashing comparison techniques. This takes a little bit more time to explain. Again, I won't go into much detail because most of you already know. A hashing function is basically a mathematical function that, provided a random input, will create a fixed length output. That's called the hash. We can call it also the fingerprint or the signature. Why? Well, basically because hashing functions have a specific property called referential transparency that basically means that provided the same input twice, the resulting hash will always be the same. It means if you have two files and when applied the hashing functions you get the same fingerprint or the same final hash, it means that both files are exactly the same. Even the slightest change in the file will produce a different hash. So what does it mean? That just by using the signatures, we can use them as a digital fingerprint of our files. If we have 1 million files and we find two files with the same signature, you are pretty sure that they are the same file. So good things about these techniques, in a nutshell, they can spot more similarities than simple plain text comparison when no obfuscation or very simple obfuscation techniques have been made. And of course, they are basically the only option left when you don't have access to the source code. But think, as just said, if you just modify a byte in a file, the hash will be different. So it renders it quite useless if someone stole your source code and doesn't give you the source code they told you you are telling them they stole. Okay, now let's change completely the topic for a while. I promise it will take only a couple of minutes, but we need this background information before going further. Let's talk about something called metadata. It's like cloud or, I don't know, security architecture or CREST. It's a trendy word. Everyone is using metadata lately. But what the hell is metadata at the end of the day? If you go to Wikipedia and search what's metadata, it gives you a very bizarre definition. It says it's data about the data. The hell. What does it mean? It means that when any kind of data is created, let's call it X, there's always some related data to that doesn't really belong to X, but is somehow associated to it, and you can use it to define X. This is a good example. For example, you have a typical Office text file. The data by itself is whatever is in the text. So you are talking about lorem ipsum $, that's the data, that's the text. But there's also always some metadata associated to it. So when did the file was created? What's the extension of the file? What's the author of that file? What's the subject? Or where was it located when you created the original file? It's not the data, but you can somehow describe the same file by using that metadata. Now let's another time change the topic. Now it's the most well-known typical executable format in Windows operating system is called PE, the typical .exe application. Yes, the average application is always formatted with the PE format. Many of you will know it well. It's basically a structured format composed of several headers, sections, and substructures that define how an application is run into the operating system. Now we can think about the PE format, the metadata. Because compiling source code into a program will always generate a PE formatted binary, it will contain always a specific set of headers and structures. So how many data can we extract from a P file? Well, a lot. This is just a diagram containing all the typical structures contained that can be you can find in a P formatted file. Now let's talk about disassembly. Disassembly or the compilation, depending on the context, is the opposite to compilation. So you have the binary, you have those zeros and ones, and you try to somehow reconstruct that binary into something like a readable source code similar to the original program. What good about it? Well, it makes the process of analyzing the program way easier, but there's always some caveat. In this case, a lot of information gets lost in the process of trying to reconstruct the original source. For example, variable names are lost. If you have created a program that with meaningful names at apple, pear, cherry, and you use the function juice for apple for creating, that doesn't appear when you try to reconstruct it because at the end of the day, the processor doesn't need that, so it will rename apple to A or 1, something as small as possible to optimize the speed of the final executable. But let's talk about more advanced features of disassemblers. They can help you on detecting the evidence of source code that has been reused because you can reconstruct the binary internal functions. Functions are always functions. So if you are relying on, say, the setlib library compression, you will have to use the function compress and uncompress and use the external DLL library, an external file that contains that function. So you can reconstruct, provided a .exe file, all of the functions and the AP calls that are being used by the application. If you find that two applications that shouldn't be related at all are using the same bunch of function calls, that gives you a good idea that they may be coming from the same source code. Another feature, very interesting about disassemblers and the compilers, is trying to reconstruct the graphic binary functions flow. So in this case, you are saying two programs after applying a small patch to one of them. You can see basically this reconstruction is for the set of functions or the set of different steps the program takes when executed. You reconstruct the different variable names are created and how different functions are called from within one place of the code to the other. If you can see that two maps of two different applications are similar, you can also get a good idea that how can it be that two unrelated programs are having the same internal structure in terms of the graphic binary functions flow. That doesn't make sense at all. That's too uncommon. So in the end, as you can see, all of this is already taking into account the metadata. It's not the data, it's not the executable, it's the internal functions, the way the structures are set, the way the sections of the PXE are being used allows you to use that metadata to spot similarities between two different files. Another metadata we can extract from the binary P structure just by looking at the headers is the architecture, Intel, ARM, Windows CE for MIPS processors, 32, 64 bits, the version, the internal version of the application, when it was created, even the compiler that was used, and if .NET is used, because of it uses an internal XML structure to define itself, it may contain even the interfaces and external classes that you can use from within another application when calling this. So you can even reconstruct the map of the different variables and functions from a .NET application that through a process called reflection. Okay, now let's revisit one of the previously discussed binary comparison techniques, hashing. As discussed, what was the main problem about hashing? That just by changing 1 byte or adding a path of 1 byte to a file, it stops working. So imagine I'm copying your file, your whatever, something you created, an image, and I just add a byte. Hashing will be different, but you'll be able to see, but the image looks exactly the same. Okay, let's have an idea. What happens if we do split the file into segments? So say we have the image and we split it in two. We'll find that one of the two segments will match and one of the two segments of the other file. So we'll be able to determine, oh, so this comes from the same place. Yeah, but what happens if you add another byte? It will be rendered useless again. So if we want to have a really interesting comparison technique, we have to create a set of hashes for each and every possible combination of bytes inside the file. Problem about that, as you can see, is that this is just a quick summary of how many hashes do you have to store in order to do that. If you have 1 byte, you just need 1 hash. But if you have 2 bytes, you need to store 3 hashes, for the first byte, for the second one, and for the 2 bytes at the same time. And that grows exponentially. So if you want to use this technique, it would certainly work, but you need a lot of space. So the main problem is that it's computationally very expensive. So it's highly recommended to use a faster, not so much accurate hash functions like MD2, MD4. For each and every file you want to compare, you create a small database of all those potential hashes. And if you find anything that matches, then you can go back and compare it with a more powerful hashing function that gives you 100% accuracy, like MD5, well, say SHA. Still, even using these partial hashes would fail if the infringing party did such a really simple obfuscation thing like control find, control replace. So I'm going to call all my functions called @, like @_. That would really destroy the use of the hashing functions. So fortunately, there are some partial solutions. The technique we are going to talk about is called context-triggered piecewise hashing, CTPH, also called as fuzzy hashing. And despite similar, it's not exactly a hashing function. What a CTPH hash will find is what is called an homology. It means a set of strings with matching characters between them that may have or not different byte sequence between them. So you can have something like, say, ABCD 1, 2, 3, ABCD potato. Yeah. The hashing function will blatantly fail, but the fuzzy hashing will say you have 2 matches between those two characters, and because this is ABCD against ABCD 1, 2, 3, ABCD potato, say at 25% or at 30% of the bytes from one sequence and the other are matching. So that's kind of called it's an homology, and it can give you a very good idea where do you have to go and dig a little bit more. But it doesn't give you the same accuracy as a real hashing function. The problem is that 2 hashing functions can mean the same source code has been used, or that they could also mean that just a very similar approach has been taken to structure the program. So either they can come from the same source code, like say called the father is the same, or they can just mean, well, someone was just using the same kind of a structure. So, as I said, it may be due to inheritance coming from the source code, or just like people want to use the same template. But a real powerful analysis technique comes when you combine the techniques. You combine the fuzzy hash and partial hashing file comparison. It can give us really, really very interesting results. Imagine we face the task of comparing 2 different files. We suspect there's IP infringement, and nevertheless, hashing says, no, they don't match. Well, let's see what happens with fuzzy hashing. We check with fuzzy hashing and said, oh, well, they don't exactly match, but they look similar. Okay, then let's go and do the same again. Well, let's create a database with all the potential slice hashes of those 2 files, 2 or several files, and compare them. That's what is called as piecewise hashing. And we can find or we cannot find a match. But what happens if we find a match? So how do you explain you have a file and you have another file that's theoretically unrelated and that matches exactly the hash of another piece of an unrelated file called B? Can someone explain that? Well, perhaps no one guessed it, I guess. But it means that someone used the most common key sequence in the world after Control-Alt-Delete, Control-C, Control-V. It means someone just copied and pasted something from one file to the other. Let's now talk about some other additional techniques. These ones are also designed specifically to take advantage of the way an application, a binary application, works. Well, binary applications, an application is a program, and a program runs. It gets executed. So when you execute a program, the contents of the binary, some parts of the contents of the binary, get into the RAM, into the memory of the computer, while the application is being run. So we can dump the RAM memory contents while the application is running, or we can alternatively keep running the application and get several dumps. That's the difference between doing a tracing or just one snapshot. Think about why should we use this? What happens if some obfuscation techniques, such as, for example, I'm running two applications, but they're running two different operating systems. And then we are not talking about just P, just the executable is a different structure. Or what happens if I'm using an encryptor, a packer, or some kind of application that scrambles the exit? We cannot go and just try to reconstruct the function calls. But the names of the functions, or the name of the buttons, or else, sometime, eventually, they will have to be in the RAM memory. So if we dump that and extract it, we can compare and get to some conclusions. Problem. Doing that must take in account that you have to mimic as much as possible the original environment where the application needs to be run. So you need a bunch of VMs, a lot of them. Because if you are giving with an application for Android 2.1, you have to have an emulator of Android 2.1 to run the application. If they give you an application for, I don't know, BlackBerry, you will need to either a BlackBerry or a BlackBerry emulator. So you need a good prepared testbed environment for doing such a thing. Let's see now a real example of this kind of comparison. This is a kind of a real case. We had two applications. Let's call them A and B. One of them, B, was suspicious of having copied the other, copied A. The analyst, we had access to only one of the application source code, only from A, and binary comparison was giving us nothing. So partial hashing techniques, fuzzy hashing, we're finding similarities. So, okay, but problem. The applications were running in two completely different architectures. And when doing a disassembly of the files to check for the function calls, one of the potentially infringing application didn't have a list of functions. They had been removed. For one, I don't know if it was an obfuscation technique or that it was an optimization from the compiler. But we didn't have that information. We didn't know what to do. So what we did, we executed the application in an emulator. In this case, it was a Windows CE embedded environment. So we ran the application and dumped the contents of the process while executing it. So we executed the application and dumped the memory contents. As we had access to the application A source code, we knew how it worked, and we knew all its function names, variables, configuration parameters, etc. Hardcode configuration, keywords, or file names are always a very interesting thing to do because sometimes if you have a default configuration file and you see it in another unrelated program, it gives you a very good hint. In this case, we found this snippet of code. Sorry. FS, new system. Basically, as you can see, this means that by default, application A contained a hardcode XML configuration file with a hard-coded password. In parallel, we extracted the ASCII strings contained in the application B rundown, And we found that the same theoretically hard-coded password only found in application A was in application B, a theoretically unrelated application for a different architecture from a different company. So client A sent us a pointer to B, application developers, and they said, oh, well, it was just a chance. And so wait a moment. You're saying that you're using a 9 characters password in an application completely unrelated to your competency application? Really? Nah, so busted in this case. Well, unfortunately, sorry, but that was the funniest part of this presentation. Sorry I warned you it was going to be boring, but well, let's follow up with some other additional techniques. As we have just said, encryption functions or obfuscation techniques within application vendors can be a problem in terms of analyzing the program. A very interesting analysis technique developed very early, not so long ago, is called aligot. Basically, this application attached to a running process hooks itself and identifies potential encryption functions into the process flow. Then we kind of do a fast thing. We generate as many potential inputs and as many potential outputs as possible, and we compare we hook to, in this case, P, and we see that it appears this message. So we try to do the same. We don't know what's P, but knowing that it could be an obfuscation or encryption technique, we use ourselves that MD5T SHA, or encryption or hashing protocols, and we see if the output is the same. If we found that, we have identified which was the specific obfuscation technique used. In this case, for example, we attach ourselves to, this was a Trojan, and we found that T encryption is being used just by hooking ourselves to the same function and checking that the result is the same as if we were using the T encryption function. Another analysis technique is quite interesting, is generating a runtime graphic of the application function flow. Credit goes to F-Secure, the antivirus guys, because they had the original idea for doing that a long time ago, 2009. So originally it wasn't more than a cool way to visualize an application running, but fortunately for everyone, the Los Alamos US security laboratory have evolved the original idea from F-Secure and created something called Beta. Beta means visualizing executables for basic analysis. They attach to the running process, and we identify, as you can see, the loops that contain the most important parts of the application flow. The good thing about this is that comparing to applications during graphical runtime while they're executing, can quickly determine which parts of the application contain similar code. In this case, we're looking at a specific Trojan, and another very good thing is that once we find where the packer, in this case a UPX packer, an obfuscation tool, is being run, we can forget about it. We see those loops, but we don't care. Once the application is uncompressed in memory, it runs like a typical application, and we can compare that against the other application. So even if someone is using a encryptor or a packer, we are just thinking about the graphic of the running process. And that's it, basically. If there's someone who didn't fall asleep, maybe you'll have thought that some of these analysis procedures may be used in some other fields. I think a good example is yesterday's Silvio Cesare presentation. He used and extend some of those ideas in a different scenario. He uses that to find source code, vulnerable legacy source code in Linux repository. But we can also think of detecting vulnerable libraries embedded into an application. If we found fuzzy hashing or a partial hashing match from one application to the other, we can spot that they are using an old library that contains a bug. Another thing is malware classification. Either at runtime or by just running a disassembler, and if we see the two or several graphic flows are similar, we can use that to categorize which malware family it belongs to. So with Zeus, the very well-known Trojan, for example, that use self-modifying code techniques, if you run this kind of tool while executing it, you'll see that once the original uncompression function is called, the rest of the application is going to look the same. So it's these techniques can be used for quickly spotting which kind of Trojan you are facing to. And finally, embedded malware. You would say, what the F word means that the hash of a Trojan is inside my PDF file or my doc file. The hell? Well, it means someone is being a little bit sneaky and trying to send you an attached Trojan or attached malware. Wow, I think I went too fast. So, any questions?